and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we begin study of our optical fiber communication channel. So, we are going to look at the modes of an optical fiber following the systematic procedure that we have already discussed at length in the previous modules. Okay. Now, optical fibers come in various types as we have seen in the earlier module. What we want to do is to keep the analysis simple, so that we get the essential idea of how to obtain the modes of the optical fiber, and this simplification is not so much as not to be useful, it is useless, because it is actually useful. Most fibers do have a profile which can be approximated by the profile that we are going to consider in this module. Okay. The index profile that we are going to consider is what is called as a step index profile. Okay. Step index profile is very similar to the slab waveguide index profile, wherein the index of the film was constant N1 and outside N1 it was N2. In the same manner, we have an optical fiber sketched here. Please note that I have only sketched the core, because I am going to assume that this cladding essentially extends all the way to infinity. So, you have this fiber which is in the form of a dielectric cylindrical rod. Okay. It has a radius a and the core is filled with a material whose refractive index is N1, but when you go to the cladding region, that is outside the core, okay, then you suddenly go, then the profile actually changes suddenly from N1 to N2. Okay. This difference between N1 and N2 actually determines the amount of modes or the number of modes that can be guided, and well, the modes are actually confined within the optical fiber core itself. Okay. One important point of difference between the slab waveguide that we have considered, the so called planar slab waveguides, to the optical fiber is that optical fiber has a different geometry. It has a cylindrical geometry, and in practice N1 and N2 are not really very largely separated, at least for the standard single mode fibers or fibers that are used for long distance communication. The value of N1 and N2 are very close to each other, okay. But that is not really the case for an integrated optical waveguide such as a slab waveguide. Of course, that is the superficial change you might in some sense think of, but the point of having a circular geometry makes our life very difficult when dealing with optical fibers, because except for a very special case, I cannot partition my modes into transverse electric and transverse magnetic. Okay. So, this is not possible because the geometry is not planar, A. B, the boundary condition that we are going to impose at the core and the cladding interface actually means that the field does not stop and become 0 at the core cladding interface, but actually continues along. Okay. So, from physical pictures, of course, this is how the mode field would look like, at least for the fundamental mode, where this is decaying outside the core, right, and then it is being guided in the cladding. This is what you would actually expect to obtain, and this is what is true for the fundamental mode, except that the fundamental mode will, in addition to having the components, it will also have the components Ez and Hz being non-zero. Of course, sometimes Hz will be larger than in magnitude corresponding to Ez, okay, and in this case you can call them as H waves, and in the other case you call them as E waves. These are older designations coming from microwave theory. Okay. So, the designations do not really worry about that, but what I was telling you is that in addition to the transverse components of the electric field and the magnetic field, you will have usually the non-zero horizontal components as well. So, in general what would happen is all 6 components, that is 3 components of electric field and 3 components of magnetic field, will be non-zero for these waves. Okay. So, that is why they are sometimes called as hybrid waves. There is no easy way of separating them into a case where Ez alone is 0 and Hz alone is 0, right. So, we do not really have this kind of a separation possible, because as I have told you, for the 2 reasons. Okay. How do we go about analyzing such a structure? Well, we do know our first step is to choose a coordinate system and in this case we are going to choose a coordinate system which is circular cylindrical coordinate system, in which any point, okay, can be described by giving the radius at which the point occurs as well as the angle with which this particular point would make on the x and y axis. Okay. So, this is the angle phi, this is the cylinder of radius r, this is the angle phi at which this point, when you project it onto the x and y axis, this is the z axis, when you project it onto the x and y axis, this would be the angle made by the line that connects to the point where you have projected the corresponding point P onto the xy plane. Let us say this is P prime, the angle this line OP prime makes with respect to the x axis is the azimuthal angle phi. Okay. And of course, to indicate the elevation or the height of the point above the xy plane, you will have to specify the z component as well. Okay. So, this is the coordinate system which is perfectly suited for the optical fibers, because optical fibers are essentially cylindrical in nature, where the radius of the core is a. Any point can be written by 3 coordinates or can be specified by 3 coordinates r, phi and z. The longitudinal coordinate in this case is again the z directed fields. So, you will have Ez and Hz, and the transverse components which would be in this particular plane, okay, will be the Er, E phi, Hr and H phi components. All these components can be functions of r, phi and z themselves. The second step, as you know, is to actually go ahead and obtain Er, E phi, Hr and H phi in terms of Ez and Hz. To do so, you again use the curl equation. So, you have del cross E equals minus j omega mu naught H, clearly because there is no j and no charges inside the optical fiber. I have not specifically kept any current in the optical fiber. I am going to assume that the dielectric medium is perfect dielectric inside as well as perfect dielectric outside. Okay. So, the curl equations will be curl of E equals minus j omega mu naught H and curl of H equals j omega epsilon 0. Now, n1 square times E in the core and n2 square times E in the cladding, correct. I am assuming the magnetic permeability to be the same in both cases. So, therefore, I do not need to worry about that, but I have this j omega epsilon 0 n1 square E and n2 square E being the right hand sides corresponding to core and cladding separately, because in the core the refractive index is n1, in the cladding the refractive index is n2. So, how do we write this curl of electric field expressions or curl of magnetic field expressions in the cylindrical coordinate system? Well, we go to the determinant idea again. Okay. In the determinant idea, you can look up any textbook of which deals with vector analysis. These are the 3 unit vectors along r, phi and z, and this is the determinant form of the equation. So, you have del by del r, del by del phi and del by del z, okay, and then you have E r, r E phi and then E z. So, this is your curl of electric field as we have written in this. If you expand this determinant out, you are going to get the expression for curl of E. Similarly, the curl of H expression would involve Hr, H phi and Hz. So, what I am going to now do is to write these equations side by side as I did for the case of the slab waveguides. Okay. So, this might take a little while to write them down. So, in case you are writing it or when you are viewing this video, and if you have a pen and paper with you, I suggest that you stop the video here and then actually write down these equations, expand the determinants and write the equations side by side, and then you can continue to look at the equations on the video. Okay. So, that will give a check that you have done this carefully correctly. We start by writing the r component, which would be 1 by r del E z by del phi. You have del E phi by del z being equal to minus j omega mu naught H r. The corresponding component for H will be this one, where you replace E by H, okay, and then you have j omega epsilon 0. I will at this point simply write this as epsilon r. I am not going to write down whether epsilon r is epsilon r1 or epsilon r2, because you can do that substitution later on. Okay. So, I am just writing this in a general media having a refractive index epsilon r. To specialize this equation to core, you substitute epsilon r by n1 square and epsilon r by n2 square for the cladding. Okay. So, the phi component will be del E r del z minus del E z by del r equals minus j omega mu naught h phi. The corresponding equation here is del h r by del z minus del h z by del r equals j omega epsilon 0 epsilon r E phi. There is another equation which I will leave as an exercise for you to write this down. Okay. This equation of course connects the z components appropriately. So, I am not writing that one, I will leave this as an exercise. Now, what is our objective? Well, we know that all these components, whether I am looking at the electric field, the transverse or the longitudinal component, or I am looking at the magnetic field longitudinal or the components, these components go with respect to z as e power minus j beta z. That is, these are the modes that are actually propagating along the z axis, and therefore, because of their propagation along the z axis, they should have the phase factor e to the power minus j beta z. At this point, please go back to slab waveguide in case you do not really understand why this e power minus j beta z comes up. Okay. But if you do understand, you notice the similarity between the analysis of the slab waveguide on one hand with the optical fibers on the other hand. The difference is in the geometry and much more complicated expressions for characteristic equation, as you will soon see either in this module or in the next module. Okay. So, you have electric field and magnetic fields going as e power minus j beta z with respect to z axis. So, therefore, their del by del z can be replaced by minus j beta. I am going to make those substitutions into these equations and obtain 1 by r del E z by del phi plus j beta E phi equals minus j omega mu naught h r. Again, this is something that you have to do it to fully appreciate that these equations are correct. Okay. So, you have j beta h phi equals j omega epsilon 0 epsilon r, this is E r component. The second equation becomes a beta, okay, and because there will be a minus on all sides, you can remove that minus sign, okay, just as we did for the slab waveguide. So, I am removing this minus sign everywhere. So, you have j beta E r plus del E z by del r equals j omega mu naught h phi. On the right hand side, again you will have the same kind of a thing. On the left hand side, you will have a minus sign because del by del z will be minus j beta. I will transpose the minus sign onto the right hand side. So, I will have j beta h r, okay, plus del h z by del r equals minus j omega epsilon 0 epsilon r E phi. Okay. The third equation anyway does not really have any del by del z term. So, to simplify that one is really no point to do that one. So, what you now need to do is to actually look at this equation, okay, and then express h r in terms of E phi and E z, and then use that equation into this second equation here, the cross coupled equation that I am showing you. Substitute for h r and simplify this equation to obtain an expression for E phi. Okay. So, the expression for h r from the above equation would be minus 1 by j omega mu naught. So, I have 1 by r del E z by del phi, okay, plus j beta E phi, no problem at this point. And when you substitute and then simplify, I leave this as an exercise to you to show that the phi component, which is a function of all three components r, phi and z, is given by minus j divided by omega square mu naught epsilon 0 epsilon r minus beta square. Okay. So, there is no surprise here in this expression, this is kind of the same thing that we have seen earlier as well, okay, times beta z 1 by r del E z by del phi minus omega mu naught del h z by del r. Pause here a little bit to understand what is going on. What we have done is to express E phi in terms of Ez and Hz as, or rather their derivatives with respect to phi and r, and of course you can do the same thing for Er, you will have to do the same thing for Hr and H phi, and this is again an exercise. I will give the answers in the assignment for you to verify, okay, but you will have to go through this Er, Hr and H phi, and this term would essentially remain the same. And please remember that these terms are to be separately written for core and cladding, right, because in the core epsilon r will be n1 square and it would be n2 square in the cladding. We can of course simplify this omega square mu naught epsilon naught n1 square by writing this as k0 square n1 square in the core, and then you have k0 square n2 square in the cladding. Okay. So, you can simplify this omega square mu naught epsilon r by rewriting them as k0 square n1 square and k0 square n2 square. Just like in the slab waveguide, the allowed values of beta will range from k0 n2 on the lower side to k0 n1 on the higher side. Okay. And of course, not all values of beta are permitted, only certain values of beta which will satisfy the characteristic equation will be permitted, and that beta has to be within this range k0 n2 to k0 n1. Okay. Just as we did for the slab waveguide, where we defined kappa f square as k0 square n1 square minus beta square, we are going to do the same thing here, but instead of calling this as kappa f, I am going to simply call this as kappa. Okay. I could have of course called it as kappa c to indicate that this is the core, but then I would also have the same letter cladding. So, I do not want to put any subscript that will confuse us, and outside the core we know that the fields are going to decay with a decay constant, let us say gamma or dependent on gamma, for which we define in a manner very similar to the slab waveguide as well. So, gamma square will be beta square minus k0 square n2 square. So, please do these exercises, these are very important for you to understand the next steps, okay, or rather at the boundary condition where you are going to derive the characteristic equation. Okay. Now, what we have here is completed on the step 2. Step 3 corresponds to our wave equation. In this case, the wave equation has to be for Ez, and the same equation will hold for Hz as well. The form of the equations are essentially the same. And what is the wave equation for Ez or Hz? Well, it turns out that you are now looking at this del cross E, right. So, you started off with del cross E with this one. So, this del cross E was equal to something like mu epsilon del square E by del t square, if I am correct. Okay. So, you can go back and then check. So, of course, that is mu 0 epsilon r. Again, Ez wave equation will have n1 square in the core and n2 square in the cladding. So, this del cross E can be written as minus del dot E plus del square E, I believe. So, this would be minus mu naught epsilon r del square E by del t square. So, I think there is a minus sign here, not a plus sign. So, please verify this for my for us. So, I am not, I don't remember the signs out here. I will set this to 0. I am going to talk more about how I can set this to 0, or whether can I set this to 0 in this for the optical fibers. It turns out in general I can't set this to 0, but only in this special case I can do so. Okay. And the wave equation therefore becomes del square, and since we are assuming all harmonic type of solutions, del square by del t square becomes minus omega square. So, then there is a plus sign here, because then the minus sign comes from this. Then you pull this omega square mu naught epsilon 0 epsilon r to the left hand side. So, you will have plus k0 square n1 square in the core. Okay. In the cladding, of course, you will have k0 square n2 square. Okay. So, this is just the core wave equation for electric field. Again, this electric field will have r component, phi component and z component. We do not want any wave equation for r and phi, because we want a wave equation for z component. Okay. So, the equation for z component will be del square plus k0 square n1 square in the core Ez equals 0. This is the Helmholtz equation. Now, brace yourself for a little bit of a mathematical problem, because del square does not have a simple form as it had for the Cartesian coordinate system. Del square in this case, okay, actually has a form which is little complicated because we are dealing with cylindrical coordinates. Okay. So, this is the del square equation that I am writing. So, 1 by r del by del r del Ez by del r, okay, plus 1 by r square del square Ez by del phi square. So, in terms of phi and z you still have the same second derivative format, but this is the complicating fellow. Okay. Then you have plus del square Ez by del z square, okay, but I know that del square by del z square can be written as minus beta square Ez, and of course, that is that minus beta square that I am going to substitute into the wave equation. So, what I have is this simplified equation which depends only on r and phi. So, this is r actually. So, please keep this in mind, these are not gammas, these are actually r, and then you have del square Ez by del phi square plus k0 square n1 square minus beta square, which of course, as what we have described can be rewritten as kappa square. Okay. So, I will do that substitution later on. So, but now it is k0 square n1 square minus beta square times Ez, which is equal to 0. This is the wave equation that we need to solve if we want to understand how Ez depends on the coordinates r and phi. Okay. This equation is what is called as a partial differential equation. Okay. In the slab waveguide we converted the partial differential equation into a ordinary differential equation because of the one dimensional dependence on the mode fields. Here it is not possible for me to avoid the PDE because this is exactly a PDE, because there are two variables and there are partial derivatives sitting in this equation. The standard way, or at least one of the simplest way to begin to see whether this PDE has a solution or not, is to employ what is called as the method of variable separation, or sometimes called as variable separable method. Okay. In the variable separable method, what we try to do is to assume that Ez actually can be written as a function only of r and a function only of phi. Okay. So, r of r is a function of a function which is named r, which depends only on the radial component r, and phi of phi is a function which depends only on phi. Of course, along z you already know e power minus j beta z, which you have already substituted, therefore, we do not need to worry about that. But now what we have is an Ez which is function of small r and small phi. We are going to write this as a product. Now, this is an assumption. Okay. It may turn out that this assumption is sufficient for us to find the solution. It may turn out that this assumption is not sufficient for us to find the solution. We will have to find this out. Luckily, these equations have been solved by mathematicians, and those equations are known to actually give you the correct solutions. Okay. So, without further ado, we will actually substitute this r of r, phi of y, and as you could have guessed, this turns out to be another exercise for you. Okay. Because this is not very difficult, it is just the tedious steps that you need to follow. So, I will anyway I will show you at least how to simplify one equation. Okay. Then the other equation is kind of very simple for you. So, what we have is 1 by r del by del r, r del Ez by del r, correct. Now, I substitute Ez equals r of r, phi of phi, and these partial derivatives are with respect to r, therefore, phi of phi can be treated as a constant when you are doing the differentiation with respect to r. So, you can put this out. So, there is a divided by r here because that is 1 by r multiplying the whole term out there. Then you have del by del r, r multiplied with. So, when you differentiate Ez with respect to r, what do you get? You will get r prime of r, where r prime is by definition del by del r of capital R. Okay. So, you have r prime, okay, and the derivative of the product r prime with respect to r is fairly simple. So, you have r double prime here plus you have r prime, because del by del r of r will be equal to 1. This needs to be multiplied with phi of phi divided by r. So, you will have r double prime plus r prime by r multiplied to phi of phi. The other term that you had 1 by r square del square Ez by del phi square is fairly simple. You can easily show that this is nothing but r of r divided by r square, that is the constant outside the differentiation, and then the second derivative of Ez with respect to phi means second derivative of phi with respect to phi, which would be phi double prime of phi. So, these two equations are what we were looking for. Now that we have them, you can combine these equations. So, I will now have an equation which tells me that r double prime plus r prime by r times phi of phi plus r of r divided by r square, and then you had phi double prime of phi plus k0 square n1 square minus beta square times r phi equals 0. Okay. Now, what we do is we divide. So, this as I have told you is an exercise. So, if you do not understand it, please go back and then do this carefully, ensure that you understand how this equation was derived. Okay. So, what we now do is we divide throughout by r phi. Of course, I am assuming that the solution does not vanish anywhere. So, this solution is not supposed to go to 0, otherwise this differentiation operation will not really work. So, when you do that, you will have 1 by r double prime plus r prime by r, okay, plus phi double prime of phi divided by phi. There is an r square here as well. So, we will keep that for the moment. Okay. So, this is phi of phi actually plus k0 square n1 square minus beta square, okay, equals 0. Now, I multiply throughout by r square. Okay. So, when I do that, when I will get r square r double prime by r plus r prime by r, okay, plus phi double prime by phi plus k0 square n1 square minus beta square times r square equals 0. Okay. So, this is the simplified equation that we now have, which we from the method of variable separable, and what we now need to do is to solve this equation. It turns out that this equation can be solved relatively easily, at least for the phi case, but in order to solve this equation in terms of small r, that is r dependence, small r dependence, you need to know something called as Bessel functions. Okay. So, before we go to the solution of these equations, when you have some time, brush up your Bessel functions, at least look at how the Bessel functions of different kinds and different orders look like. You have Bessel function of the first kind j, you have Bessel functions of the second kind, then you have the linear combinations of those, and you can actually look at those equations. Okay. We will be using only first kind with j and first kind of type 2, which is y. Okay. So, these Bessel functions are necessary because that is how the fields are going to depend on r. With respect to phi, the equation is kind of simple. So, in the next module we are going to solve this equation. Thank you very much.